Just let me know. Okay, we have discussed last week about direct current, yeah? About the current exactly. So if in general, if we have something like this cylindrical material, if we connect it with the battery or source of voltage, something like that, then there will be a current, okay, around this cylindrical material. And we have the definition of the current is the integral G vector dot dA, okay, it's also a vector. And in general, in the material, this current density it depends on the number of charges, chargers, and also this density number of charge, this little n, this E usually the electron unit charge, okay, then Vd, the vector D is the drift velocity, okay. The drift velocity is the order of 10 to the minus 4 yeah, meter per second. It's very, very slow. And we have also discussed about Ohm's law. It states that in Ohm's law that the current density is proportional to the external electric field. Yeah. So this external means, so proportional means that the exact form is equals to sigma times E, where sigma is the conductivity of the material. And this conductivity is equal to 1 over rho. Rho, we call it resistivity. And also, we could derive that this resistivity is related to the geometry of the resistance, we call it, yeah, the geometry of the material. For example, if the cylinder or rectangular, yeah, it also depends, yeah, on this material and also this rho. Okay, so what I want to discuss today is power in, let's see. Power in resistance. So the resistance in the circuit symbolized like this. Okay, this is R here. This is resistance. Okay. If it connects to some source of voltage, there will be a current, let's say I here. You see that from the definition of work, this is equal to, let's say, dq times V, okay? This is potential functional. Okay. Function of voltage, something like that, voltage. And this is equals to, if we, sorry, maybe I should write, this is this slash E, energy. Okay. And this is equal to VI times PT, okay? So power P means is the energy. Okay, let's say W. Okay, it's W. W dt. And this is V equal V times I. Okay, but from above we get that VI is equal to I times R. Okay, so this is E squared times R. So this is the potential, we call it potential loss. Oh, no, sorry, not potential, sorry, energy loss in resistance. Okay, so the device component, example, maybe example is resistance, maybe. Example E. Example of resistance. First, we call it Selin, can you ask Muhammad Arasha whether he has a problem with the connection or?
Sorry, he said he had a stomachache.
Okay. So this is resistors. And then, well, many things. For example, lamps. Okay, lamps also symbolize like this. Okay, sorry. Yeah, it's similar like the resistor. This one. What does that mean? This energy loss, this P equals to E squared R. What does it mean? So, for example, if you have a lamp, for example, let's say a lamp like this. Okay, this is a lamp. If it's connected by say this source of voltage epsilon, there will be a current. Okay, you have a lamp here. So if you turn on the lamp, connect the lamp with this voltage source for several times, let's say for 5 minutes. Then the lamps becomes what is it? It's not hot, but less than hot. What does it mean? Warmer. Okay, this indicates, sorry. So this warm, this related to the heat, okay, the heat transfer, something like that. So this the proof that this energy loss. Okay. So it means that the energy loss is equal to this one. It's related to this heat here. This heat, the power is heat. in the resistance. For example, resistors in the resistance or lamp. Any question? Any question? Any question? No. Okay. No question. Okay. Let's continue the material. Okay, let's just discuss about circuit. Circuit. Okay, so we have discussed about resistance, yeah, resistors, capacitors, anything else? Yeah, voltage, electromotive force is like a voltage source, something like that. So circuit means that we have connect, for example, the source of the voltage called EMF, electromotive force. It's like a battery, for example, etc. This for there are so many. It's symbolized like this. This is minus, as you know, this is plus. Then it connects, for example, with the resistor. The resistor, this one. Okay, this is R. This is epsilon. Just like this, okay? This is called loop. Let's say loop. So circuit is like this. For example, this is A. What? This is R, this is epsilon, and this is, for example, B. Okay? So usually we have a current, for example, to that direction. Okay, so this is an open circuit. We call this open circuit. This loop here, this closed circuit. Electric circuit means, not Formula One. Okay. So there will be a current here, for example, I. Okay. As you know, if this is, let's say this A and B, VAB is equal to I times R, okay? As you know intuitively, if this one is equal to, we put like this, equivalently, we can say that we can also take this A here and B here, okay? So this is equal to epsilon, okay? So we could, let's say, epsilon minus IR equal to 0. So this is the simple, or this one is the simple result from closed circuit. Okay. So what happened between the potential between the resistor? For example, I took again from A to B. What happened? What happened? So there will be, so which one is greater, from VA or VB? Which one greater in the potential? Sorry, in the resistor.
VA.
Yeah.
Yeah, VA is greater than VB. Okay, so that's why this P here is equal to IVAB. Okay, so this is because minus is VAB. Sorry. Oh, sorry, VAB. It means, sorry, it's VA means VB. Okay, so it should be positive. So this is, sorry, okay. So this is the power loss. Yeah. So I want to share something to you. You can see from, if you have a Halliday-Resnick book, let's see, you can open page page 709. Okay, this one. You can see from this figure 27 strip 4. So here we have this little r here is the internal resistance, okay, of the battery or electromotive force. This capital R here is the external resistance, okay. You see that this is from this minus pole, from 0, then become positive, and then it drops when after passing this internal resistance, and then it drops again the potential to 0 after passing through this this external resistance, yeah, capital R. Okay, that's why this potential VA here is the same, yeah, the same as 0. So this is for the closed loop. Okay. Anything else? Any question? No? Okay. Let's go back to this whiteboard.
Sir?
Yes?
Sorry to interrupt, but I think Riandito is in the waiting room. He changed device.
Oh, okay. Okay, yeah. Done. Any question?
Thank you, sir.
Okay. So for this is for the closed circuit, yeah. Closed circuit. Let's say this VA here. We could say that for the closed circuit, we have, for example, if this is A here, we have VA times IR, okay? This, so for example, we take the loop, something like this, okay? So this is plus because the loop, so the current is in the same direction as the loop, okay? So this is plus, and then this equals 2. So from this one to A, and then we get to this point, this negative pole here. So this is positive, the convention. And then we go back again to this VA, sorry. Then we get this relation. Okay. Okay, this is for the closed circuit. What about for open circuit like this? What about the open circuit like this? Which one is the greater one? VA or VB? Which one is greater? Hello, hello.
In this case, VB, I think.
VB. Hello, hello.
Yes, sir.
Okay. Anything else? Reno?
Yes, sir.
Yeah. Which one the voltage is greater? VA or VB?
I think VB, sir.
Why? Do you know the reason? Can you say the reason?
I'm not sure, but I'm pretty sure it's VB because it's an open circuit rather than a closed one.
Okay. Riandito.
Yes, sir.
Yeah. Which one is greater?
I also think it's PB. From
VB.
Yeah.
VB. Hello, hello.
Hello.
Yes.
Sir.
Yes.
I think.
Which one is greater?
I think it's PB because there's a resistance.
Okay. Yeah.
Is it VB has no current runs to VA?
Okay. 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 Most of you answer VB. Let's see. So the current is through there. Okay. So the current, the direction of the current is the direction of positive charge. Okay. Positive charge. Which one? Okay. Positive charge. So positive charge, you can say. So positive charge flows through, let's say, this is a minus, this is a plus, and this is minus, let's say, or this is plus, or this is 0. which means that it flows from the higher voltage to the lower voltage. So it means that VA is greater than VB. Okay? If we know the direction of the current. Okay? If the other way around, this one, okay, this should be VB greater than VA. Okay? Hello, hello?
Oh, okay. Okay.
Yes, sir. Okay, yeah.
Okay. If you know the direction of the currents, yeah. Okay. So the currents, the direction of the currents is the same as the direction of the positive charge flow through the wire. Okay, it's the same. So it means that if the positive charge move, for example, to the right, it means that the right hand side, the voltage is lower than the left hand side. Okay, that's for open circuit, because open circuits you can connect with anything. There is also a resistor or capacitor or EMF or battery, something like that. Okay, on the circuit, there is two laws. On circuit, there is so-called Kirchhoff's law. So there are two points here. The first one is the number of charges is conserved on the circuit. Yeah, is conserved. Conserve. What does it mean? If we have like this, let's say this is I1, I2, I3, I4, I5. This is called a junction. Junction. Junction or vertex. So the current before passing through the junction is equal to the summation of the total current after passing through this junction. Okay, this is happens. This is holds, or this is satisfied because this one. The number of charges on the circuit is conserved. Okay, so now this is on. This in the circuit. Okay. Number two. So-called the conservation of energy. So the conservation of energy, so it means that the energy in the circuit is also conserved. So for example, in the simple circuit, as we have discussed before, this one, okay, it should be epsilon equal to IR. So if there are so many, there are n tuple of this epsilon equals also the number of the resistor. And also if there is anything, for example, capacitor, or there are other devices than this one, and this is valid. Okay. The example is this one, this simple circuit, yeah, battery and this capital R, this resistor. I will refer back for this one for a book. Yeah. Let's see. For example, this one, yeah. Maybe before this one. So this one again, for example, if the battery, for example, or this what we call it? Yeah, the battery or the voltage source have internal resistance. Yeah. In the figure 27 minus 6. Okay. So, for example, in the so we, for example, if we use is like this, yeah, this 27/6, we get okay, this one, for example. This is little r, this is epsilon, and this is r, okay? So there is I here, for example. I here, because we talk about direct current, so this is a constant, okay? So how many epsilon here? Only one, okay? One. And how many resistor? We have two, okay? So it should be this I little r times I capital R. So the current should be epsilon over R plus this one. Okay. Oh yes. We choose the loop like this. So the loop usually we usually we give with a point, for example, this one, this A, B, C, D. Okay, the loop is A, B, C, D, A. Okay, we have like this. We have like this. What about if we choose the loop the other way around? A, B, C, B, A. So this is this one, this is this one. So if this one we take this because the other way around, so we start with this positive pole, yeah, of the battery. So it should be minus epsilon. And then because the direction of the loop is opposite of the direction of this current, it should be minus, okay? Sorry, this is I, capital I, R. Minus I, capital R, okay? So we get the same result again as above. So you can take anything, any loop, any direction. Yeah. Any question? So this is number one. Number two, it will be more complicated like this. For example, we have this one. Sorry, it's look like capacitor. This one. We have this one. We have we have epsilon 1, R1, epsilon 2, R2, epsilon 3, R3. You can give the corner there. A, B, C, D, E, F. How many loops here? Simple question, how many loops?
2.
So let's say identify, yeah? Let's say identify. A, B, C, E, F, A. Okay? Then we get B, C, D, E, B, C, D, E, B. Okay? And we get also A, B, C, D, E, F, A. Anything? Any?
A, B, E, F, A.
A, B, E, F, A. Already. This one.
But
A, B. Oh, sorry. Yeah. It's already here. A, B, C. Sorry. It should be, I'm sorry. Yeah, you're right. A, B, E, F, A. Okay. A, B, F, A. B, C, D, E, B. A, B, C, D, E, F, E. Okay. F, A, sorry. So we have 3, yeah? We have 3. How about this one? So we can make an assumption. Suppose that we have this I1, I2, sorry, not I2, I3. I3, this is, let's say, I2, okay? So from the direction of the current, we could have I1 equals to I2 plus I3, okay? This is for first Kirchhoff law, okay? First Kirchhoff law. Let's say we suppose that the direction, we take the direction of this, of currents, of all currents like this, okay? If the current we get, for example, is positive, then we have the correct direction, okay? If we get the current, the value of the current is negative, then, for example, like this, so if the current is negative, then the direction is the opposite, okay? The other way around, okay? So if we analyze, for example, the first loops, for example, what we get? A, B, C, D. How many number of voltage source or MF? The battery, only one, okay? For A, B, C, A, B, E, F, A, so we get from here to here. Okay, so it be positive. Okay, and then this E1, sorry, A, B, E, F, A, we have two batteries, okay? The other way around is this one, yeah? And then also this one, so it should be positive. Okay, this equals to I1, R1 plus I2, R2. Okay. What about this one? B, C, D, E, B. Okay, B, C, D. Okay, we get this is this one, so it should be negative. Okay. Then to this one, again negative. So this is, so the current is in the same direction as the loop. Yeah. Okay, so this is, oh sorry, this I3 is positive times R3, but I2 is the opposite. Yeah. So this is minus I2 R2. Okay. What about this one? The last one. A, B, C, D, E, F. A. Again, we get the positive epsilon 1 minus epsilon 3 equals to I1, sorry, I1 times R1 this one, yeah, okay, plus I3 R3. Any question? Any question?
Not yet, sir.
Okay, I will summarize our lecture today. Oh, sorry. Okay, not yet. We have until 11:45, yeah. Okay. 11:45. Sorry. 1 more hours. Any question? Any question?
On the right, why is it clockwise?
Loop on the right. Well, I choose the direction of the route. I choose the direction of the loop, anything I want. I mean, it depends on you. I mean, you could do the other way around. I mean, the opposite direction.
Okay, sir. Thank you.
Yeah. It depends how you take the loop.
Sir?
Yes?
If our assumption of the loop is like, let's say, negative, is it recommended for us to turn it back to positive?
Sorry.
If our assumption of the loop, like whether it's clockwise or counterclockwise, results in a negative, is it recommendable? Is it recommended for us to turn it into a positive?
Well, if you get, for example, the negative result, for example, for current, you mean?
Yes, sir.
Yeah, for the current, I mean, you don't have to. I mean, you just said that, I mean, the direction of the current is the opposite one. I mean, the opposite of the direction you have taken.
All right, understandable.
Okay. I mean, it's not necessary whether you take the loop clockwise or counterclockwise. Well, you could also have this negative result, for example, in counterclockwise. It depends on the problem. But you don't have to worry about this result, because if you get, for example, the current becomes negative, then you should take the direction of the current is opposite to the loop. Anything else? Okay, let's, if you have holiday resnick, you can read or you can open page number 714 about parallel resistance in parallel circuit. Let me stop here first.
27-7, right, sir?
714, holiday resnick.
Yes.
No, sir, no. Yeah, 714. 714, I think. This one. Okay. This is in parallel circuit. Something like this in figure 2710. Okay, you see this one? So this is, we have a parallel circuit of the combination between this voltage source and the parallel circuit of resistance, okay, or resistors. Okay, so in this case, we this figure 2710A, three resistors in parallel is equivalent to this REQ, capital RQ, capital REQ, means this the equivalence resistance. Okay, so this can be computed. So in the parallel circuit, the voltage is the same for all resistors. Okay, R1, capital R1, capital R2, and capital R3. So this the current which is passing through this R1, I1 equals to V over R1, I2, etc. Okay. So the total current in the circuit is the summation of I1, I2, and I3. Okay. And then from the above formulae, we could get that this 2721, equation 2721, yeah, we could cast into equation 27, 22, yeah, where 1 over RQ is equal to this 27, 23. So this is there if there are 3 resistors or 3 resistance. Okay. If there are many, for example, n resistance in parallel or resistors, okay, so you just 1 over Rj. J is time is J from 1 to n. Okay. So this is the parallel. What about serial? Serial is easier. Serial is for the resistor is the summation of R1, R2, etc. until Rn. If there are n numbers of resistors or resistance, okay? And this is also the parallel one, okay? This is the left table. The left table is for resistor, and for capacitors, it's opposite, yeah. I mean, this for serial circuit, we get this 25, 22, and then for a capacitor in parallel, we get the summation of the capacitors. So this is the same current in the serial circuit with the same current. In parallel, we have the same potential difference. And then in the series, for capacitor, we have the same charge. Yeah. Also in capacitor, we have the same potential difference across all capacitors. Any question? Okay. Let's go to the example. This is not really complicated. This one. Okay, this one. Yeah. This is similar to our case. Okay. So figure 27, strip 13. We have two voltage source, two batteries. Epsilon 1 is 3 volt and epsilon 2 is 6 volt, okay? R1 is 2 ohms, R2 is 4 ohms, okay? And the figure like this. So epsilon 1, we have 1 in the circuit, okay? And the E2, yeah, we have 2 batteries, yeah, E2. Okay. Which 719, okay, 719. 719, okay. So you can see if you have if you have a book, okay. In the book, the author take assumption that E1, the direction is to the right, and then E2 to the left, and then I3 to from above to below, yeah, to below. Okay. So the question is, find the magnitude and the direction of the current in each of these three branches. Is there anything not clear for you for this sample problem? Okay, let's stop. Let's say, okay. This is example 3. We have epsilon 1, epsilon 2. This is, sorry. Okay. This is R1. So this is R1. Okay. And this is R2. This is point A. This is point B. Okay. We took the direction of loops. This is I1, I2, I3, okay? So I3 is equals to I1 plus I2, okay? Let's say what we call it, yeah, A, B, C, D, E, F, okay? First loop, yeah. First loop D, A, B, C, D. Okay, this one. Yeah. What we get? So just using this one. Okay. So how many batteries. We have 2, okay? So this one is epsilon 1, and then this is positive, so this is minus epsilon 2. Okay? So this is equals to, you see that because the direction of the current is the same as the loop, so it means that we have a positive here, I1, R1 plus I3, R2 plus I1, R1. Okay? Sorry, this epsilon 1 is 3 volts. Epsilon 2 is 6 volt. R1 2 ohms. And then R2 is 4 ohms here. Okay. If we calculate, so this should be 3 minus 6 equals to I1. What is R1? 2. This is I3. This is 4 plus I1, 2. Okay, this should be 4I1 plus 4I3 equals to minus 3. Okay. Then we get right-hand loop. Okay. Loop A, E, F, B, A. A, E, F, B, A. Okay, this one again. So we have sigma epsilon equals sigma IR. Okay, okay, for this one, we have E2. Okay, this is positive. Okay, this is positive. To this one, okay, this is negative. Equals to. So because the direction of the current is opposite, yeah, to the direction of the loop, so it should be minus I2 R1. Okay. Should be minus I2 R1 minus I3 R3. Sorry, this one. Okay. Sorry. This is R3 R2. Sorry. So this is 3 minus 3 equals minus I2. R1 is 2, okay? Minus 2 minus I3, 4. Okay? So this becomes 0, sorry. Let's say this is minus 4I2 minus 4I3 equals 0. Okay, then we get this I2 plus I3 equals to 0. Means that I2 is minus I3. Okay? So we get this one and this one. Okay, any question? So if we take, because we have this relation here, this, sorry, what is the relation? I3 equals to I1 plus I2, okay? If we insert this relation to this one, then we get, let's say, I3 is minus 2, I2, okay? So it should be minus I2 equals to I1 plus I2, okay? So it should be I2 is minus I1 over 2. Anything else? Any question?
Is
So
this
it's,
only
yes?
is this only calculating the left-hand loop and the right-hand loop?
Yeah. You
So
could also consider the biggest loop here. The biggest loop is D, E, D, A, E, F, B, C, D. You could also, but this is the simplest thing, I think. Okay, anything else? Okay, let's continue. So it means that this I3 equals to I1 over 2, okay? Sorry, just a second. Is it I3 is minus, yeah, okay. I3 is minus I2, okay. I2 is minus I1 over 2. So it means that I3 is equals to I1 over 2, okay. So if we insert this relation, for example, to this one, okay, what we get is that 4I1 plus 4I1 over 2 equals minus 3. So we get that 6I1 minus 3. So we get I1, I1 is minus 1.5 ampere. Okay. It means that this is a minus here, okay? It means our assumption well, let's say not correct. So the direction of I1 is opposite, yeah, to our assumption. Okay. What about So I3 is I1 over 2. So this should be minus 1/4, a quarter ampere. What about I2? I2, which one? I2 is minus, okay. I2 I2 is minus I3, okay, so it should be a quarter ampere. Okay, this one. So the direction of this I2 is already correct, okay? So we have to correct the direction. So the direction of this I1 and I3 is the opposite of our assumption. Yeah, assumption. So it should be so if we correct, let's say this is R1, epsilon 1, R1. This is one R2, yeah, and this is epsilon 2. This is epsilon 2. Okay, yeah. So the correct one is I1 and I3. I1 and I3. I1 and I3. So it should be like this. This is I1. This is I3. And this is I2. Okay. So this is the correct direction of this current for I1 and I3 because we have a minus here. Okay. Any question? This is A. Sorry. This is A. This is B. Anything else? Any question? Okay, how to calculate the voltage? So the question is how to calculate the voltage VAB. VAB. Let's say this is, I said that VAB is VA minus VB. Or the other way around. VAB. Oh yes, VAB here, yeah. VAB. Okay. VAB. Where is it? Okay. VA minus VB. How about this one? So you see that if we start from this point to this point and then to this point, okay? So this VB here equals to epsilon just 1 second, okay, epsilon plus I3 R2, okay, so plus VA, okay. So it should be VB minus VA is epsilon plus I3 R2. Okay, so it should be equals to minus VAB. So VAB is minus epsilon minus I3. Okay? Anything?
Yes, it's good.
Hello, yeah? Hello? Any question? I cannot hear you. Hello? Hello, any question? I cannot hear you. Which one of you is already spoke? Hello, any question so far? Hello, hello?
No, sir, I think it's clear.
Is it clear or not clear?
It's clear.
Okay. Sorry, I forgot something. So if we took this one, so this is before that, this is minus and plus, okay? This one, so it should be, there is a minus here, and then there is a minus here. So this is plus here. Okay, we compute this epsilon. Sorry, this is epsilon 2, yeah. Sorry, this is epsilon 2 again. Sorry. Epsilon 2, epsilon 2. So this is sorry, which one? Epsilon 2 is 6-fold minus R3, which R3 is a quarter. Sorry, I3 is quarter, yeah. Quarter. A quarter times R2, 4. Okay, So it should be 5 volts. Okay. So this should be VA minus B, because VA should be VA, it should be less, yeah. So this is, I've told you before, this VA should be less than VB, okay? So this should be negative here. Okay. So, okay, sorry for this mistake. This is plus and this is minus here. Should be minus here. So, yeah, the other way around. Sorry. Should be epsilon 2 should be minus. So it should be minus plus, it would be minus here. Should be minus. Minus 5 volt. Okay. Sorry about that. So you see that this FB is 5 plus VB. Okay. So because we have the direction like this, okay, from B to A, so it should be the potential VA is less than potential VB. Sorry about that. Yeah. Any question? Any question?
Sir, can I ask a question? In
Yes.
the VB is equal to epsilon 2 minus I3 R2. Are the signs chosen because the loop is clockwise?
The loop is clockwise. Yes, why?
Is that where the sign come from, the minus plus? Is that how we determine it?
Oh, yeah. Because I already correct this, the loop. I mean, this is the correct one. So in this case, I took I3 is quarter ampere, and I2 is quarter also, yeah. Okay. Quarter also. Everything is positive here. I1 is I1 is 1/2. Yeah. I already take this. Everything is positive. So we know that this, if this is the case, then I mean the how to calculate the potential is like this. Epsilon 2, we've met first with this epsilon 2, the negative should be positive here, and then because there is potential loss here, sorry, the power loss here should be minus here. But this is for the correct one. Yeah, I mean, you say that, we could say that this is the loop, for example, like this. If we take, for example, still negative, we could say that for this negative, yeah, this the other way around, I think. This VA, this assumption, VA minus, sorry, VA minus R3 R minus epsilon 2 plus VB. So this is VA is minus, this is R2, yeah. R2 is 4, right? Minus 6 plus VB. Okay. If this is VA minus 5 plus VB. Okay, we get the same answer. Like that. Okay.
Yeah, that's okay. Makes sense.
Yeah. Okay, anything else? Okay, I will speak in Indonesia ya for the last 10 minutes.
Oh ya, boleh Pak.
Okay. So, kita udah diskusi ya. Pertama terkait dengan mana tadi? Terkait dengan ini apa daya pada resistor ya. Jadi artinya sebenarnya ini daya yang hilang ya sebenarnya. Jadi kalau misalkan kita ambil rangkaian yang sederhana saja, itu yang terdiri dari baterai ya dengan resistor ya, ini ada arus I besar yang mengalir gitu ya. Nah, D coret di sini, D strip di sini itu maksudnya jumlah energi ya, jumlah energi itu yang hilang itu adalah dq kali V. V di situ sebutnya potensial atau beda potensial. Kalau kita lihat I di sini kan sama dengan dq per dt. Ya. I di sini kan sama dengan dq per dt ya. Sehingga nanti bisa saya tulis jadi seperti ini. Dan kalau saya bagi dw per dt itu adalah V kali I yang sama dengan I kuadrat kali R. Ini dikatakan energi loss atau energi yang hilang ya dalam resistor gitu ya, dalam hambatan. Nah, hambatan itu biasanya contoh-contohnya berupa resistor, komponen, atau lampu misalkan ya. Jadi kalau Anda misalkan nyalakan ke saklar lampu tersebut, ya, misalkan selama 5 menit gitu ya, kemudian Anda matikan lagi, lampu itu akan terasa panas. Gitu. Artinya kenapa? Itu ada energi yang hilang di situ. Nah, energi yang hilang itu biasanya kalau untuk di lampu, itu digunakan untuk apa? Untuk menghasilkan cahaya di situ. Karena di situ kan ada gas-gas gitu ya. Jadi energi yang hilang itu belum tentu hilang itu dalam artian rugi, tidak. Tapi konteksnya itu adalah itu memanfaatkan energi kan, ada pencahayaan. Itu terkait dengan untung ruginya. Kalau misalkan kalau di situ mungkin untung ya, kalau ruginya itu misalkan begini. Biasanya kalau PLN itu misalkan mengirimkan sebuah pulsa istilahnya namanya pulsa listrik yang berupa gelombang elektromagnetik itu melalui kabel yang istilahnya yang tegangannya sangat tinggi gitu ya, kabel khusus gitu. Nah, itu biasanya ada energi loss di situ. Akibat apa? Akibat sifat resistansi alami dari kabelnya. Nah, kalau energi loss di situ itu berarti terkait dengan kerugian gitu kan. Istilahnya PLN sudah menghasilkan misalkan ya dayanya itu 500 megawatt. ketika dikirim itu bisa loss, bisa mungkin 20-30% lossnya ya. Itu kan kalau daya itu bisa menjadi 70% ya, jadi dari 500 misalkan jadi 350 megawatt gitu ya, sampai sini. Nah itu kan artinya ada yang hilang di situ kan, 150 megawatt gitu kan. Kalau 150 megawatt itu dihitung berapa dalam dolar atau dalam rupiah gitu ya. Itu bisa miliar sampai triliunan gitu ya. Jadi kalau itu kita berbicara konteks hambatan dalam kerugian gitu ya. Jadi nah makanya ada teknologi dalam arus kuat itu bagaimana supaya daya yang hilang itu tidak besar. Nah biasanya itu nanti di antara tengah-tengah dari istilahnya misalkan dari 100 km di tengah-tengahnya atau tiap 25 km itu dikasih kayak repeater gitu, pembangkit tegangan ya secara alami. Itu nanti akan kita bahas itu terkait dengan transformator gitu ya, yang merubah tegangan sehingga arus daya yang hilang itu tidak besar gitu ya. Seperti itu. Nah, itu dari sisi power loss. Nah, sekarang kita bahas juga tentang sirkuit ya. Jadi sirkuit sederhana misalkan seperti tadi ini ada dalam sirkuit sederhana ya. Ini kita sebut namanya loop. Loop itu adalah yang tertutup dia. Jadi ya seperti ini gambarnya. Kalau yang misalkan ada loop rangkaian terbuka, ini rangkaian tertutup yang kita sebut loop yang sebelah kiri. Yang sebelah kanan ini adalah open circuit atau sirkuit terbuka. Dan potensialnya antara A dan B itu sama gitu ya. Kalau di sini A dengan B-nya berhimpit gitu ya. Jadi sama gitu. Jadi tidak ada beda tegangan, kalau di sini ada beda tegangan. Nah kemarin tadi juga kita bahas bahwa kalau misalkan arusnya itu arahnya ke kanan, itu berarti arus itu kan terkait dengan arah alir muatan positif. Gitu. Jadi kalau namanya muatan positif, itu mengalir dari yang positif, tegangan tinggi ke tegangan rendah. Gitu. Kuncinya itu, selalu seperti itu. Arus itu adalah dari tegangan tinggi ke rendah. Ngeceknya gitu aja, itu konsep penting. Jadi kalau misalkan arusnya ke kanan itu berarti VA itu lebih besar daripada VB kan. Jadi karena dia dari tegangan tinggi ke rendah. Kalau sebaliknya ya tadi, kalau sebaliknya berarti VB yang tinggi, ya, VA yang rendah seperti itu. Kemudian dalam sirkuit itu tuh berlaku hukum Kirchhoff namanya. Hukum Kirchhoff itu ada poin 1 dan 2, hukum Kirchhoff 1 Kirchhoff dan 2 Kirchhoff. Hukum 1 Kirchhoff itu terkait dengan kekalahan muatan. Jadi muatan dalam rangkaian itu bersifat kekal, gitu, conserve gitu ya. Nah, muatan itu bisa jadi berkurang seiring dengan waktu, tapi dia berubah menjadi energi, biasanya diserap gitu ya, sama bahan ya. Nah, jadi kalau kita ambil kasus kita, ini berlaku ya, jumlahan arus sebelum melewati junction atau titik vertex itu sama jumlahnya arusnya gitu. Jadi itu namanya muatannya conserve antara awal dengan akhir. Kemudian yang kedua itu adalah hukum kekalahan energi ya, dalam muatan. Nah itu biasanya terkait dengan tegangan. Jadi biasanya tegangan awal dengan akhir itu sama kita ambilnya, tidak ada loss di situ. Ini sebenarnya kasus ideal sebenarnya. Tapi maksud saya walaupun energinya itu bisa loss, tapi dia bisa juga terkait dengan energi hilang itu terkait dengan tadi. Kita memperhitungkan disipatif dari sifat bahannya, tapi itu ditambah lagi. Tapi dalam hal ini kita biasanya itu masuknya ke hambatan. Nah, jadi kalau kekalahan energi itu bisa dinyatakan sebagai jumlahan dari baterai ya sama dengan jumlahan dari arus ditambah tegangan ya. Tegangan misalkan dari kapasitor atau yang lain. Ini saya ambil contoh misalkan untuk sirkuit sederhana gitu ya, dengan satu R kecil atau hambatan dalam, satu lagi R besar itu adalah hambatan luar ya gitu. Itu bisa kita dapatkan arusnya itu dihitung seperti ini. Kemudian ini satu loop. Nah sekarang kalau misalkan ada seperti ini gimana? Ini ada 3 loop berarti kan. Ada A, B, C, D, E, F, G, E, F, A gitu ya. Ada A, B, E, F, A, ada B, C, D, E, B, ada A, B, C, D, E, F, A. Jadi ini ada tiga loops gitu ya. Nah, jadi kalau arusnya nanti kita perhitungan itu kita dapatkan positif, itu berarti pemisalan kita itu betul. Ya, misalkan I1-nya itu positif, berarti betul arahnya ke sana. Kalau itu negatif, itu berarti arahnya tinggal dibalik aja berlawanan. Nah, kemudian kita ambil contoh lagi untuk yang tadi 3 loop yang atas, cuma dia spesifik. Kita ambil ada epsilon 1 dan epsilon 2, R1 dan R2 seperti ini. Ya, dan ternyata kita dapatkan, kita cukup mengambil 2 loop ya. Loop kiri dan kanan, itu kita dapatkan bahwa persamaan-persamaannya dipecahkan, itu dapatkan I1 sama dengan minus. Itu artinya asumsi kita yang tadi istilahnya arah arusnya ke sana, itu berarti arahnya ke kiri gitu. Atau berlawanan arah dengan jarum jam lah kalau ininya. Jadi I1 itu negatif seperti itu. Kemudian kalau I3-nya itu ternyata dia juga negatif. Itu artinya dia bukan ke bawah tapi ke atas ya. Yang seperti ini. Maaf. Yang seperti ini ya. Jadi dia itu negatif ke atas. Nah, yang sudah benar itu adalah I2 gitu ya. Jadi yang benar itu adalah I1 sama dengan I2 plus I3 gitu. Bukan I3 sama dengan I1 plus I2. Cuma itu aja. Tapi nanti dalam ada pengerjaan soal, kalau itu dapat tanda minus, itu tidak salah, itu benar. Cuma tandanya arahnya aja terbalik. Kemudian kita meninjau bagaimana menghitung VAB. Nah, ini kita lihat di sini. Kalau arah arus I3-nya itu kan ke atas. Itu berarti VB-nya itu lebih besar dibanding dengan VA, atau VA lebih kecil dari VB. Makanya kita harus kadang-kala istilahnya dalam tanda kutip cukup cerdik gitu ya, dengan menganggap konsep yang sederhana ini, itu kita bisa memilih ini kira-kira mana yang cocok tandanya. Nah, yang cocok itu kebetulan epsilon 2 ketika masuk ya kan dia ketemu negatif, tapi di sini diambil positif. Untuk negatif tapi ini positif. Kemudian di sini di resistor dia ambilnya minus ya. Karena biasanya resistor itu dia sifatnya kan ada disipatif gitu ya. Jadi makanya di sini minus. Ada pengurangan tegangan di sana. Makanya di sini minus. Kemudian ditambah VA gitu ya. Nah, kalau udah tambah minus gini berarti udah jelas kan, berarti VB itu pasti lebih besar daripada VA dalam hal ini. Nah, jadi kalau kita hitung VAB ternyata memang betul dia itu adalah minus ya, minus 5 volt, oke. Untuk kita dapatkan VB sama dengan 5 tambah VA gitu. Nah, tadi ada pertanyaan di teman Anda, bagaimana kalau misalkan saya nggak ngerubah ini? Nah, sama. Jadi kalau kita tidak merubah, artinya I3-nya itu masih negatif ke bawah, sama. Yang di sini juga negatif I3. Cuma nanti yang membedakan itu ada di sininya. Ada di epsilon 2-nya. Dia tuh yang tadinya di sininya positif, ya, itu jadi negatif, dia ditambah VB. Gitu. Ini didapatkan bahwa VA itu sama dengan minus 5 VB. Jadi kita juga mendapatkan kesimpulan yang sama bahwa VB itu sama dengan VA ditambah 5 ya, satuannya volt. Mungkin itu aja dari saya, kecuali ada pertanyaan, silakan. Tidak ada pertanyaan? Oke, kalau tidak ada, kita akhiri ya. Jangan lupa absen ya. Saya itu settingnya sampai jam 12. Ya. Besok mungkin kita bahas tentang, besok kita bahas tentang kemungkinan tentang gaya Lorentz atau rangkaian RC kayaknya ya. Sebentar rangkaian RC, kemudian ada gaya Lorentz. Oke. Itu saja. Terus juga itu ada kuesioner yang saya kasih di Teams, itu tolong diisi ya. Oke, terima kasih
Itu
semuanya.
kayak
Oke.
itu kayak survei apa, Pak?
Ya, survei ya. Tolong itu diisi.
Oke, makasih Pak. Thank you.
Untuk
Makasih,
feedback
Pak.
kita. Ya, sama-sama. Oke,
Makasih,
terima
Pak.
kasih. Kesehatan semua.